So the bicarb ion is going to be the one that is very important for transporting CO2. A little bit will move on to the red blood cell, a hemoglobin. A little bit will be in the plasma, but the majority of the way that we are going to have CO2 travel is the bicarb ion. Yes, no, maybe. So the hemoglobin molecule. What do you notice about it? First of all, let's break it down a little bit. How do we form protein?
Through amino acids.
The amino acids. What codes for the amino acids? Our DNA, the gene on that DNA. So now, when I look at this picture right here, they're trying to show me, do you guys remember how when we had the string of amino acids to make a protein, that when the protein gets made, proteins have primary, secondary, tertiary structure, okay? And then if we get to the tertiary structure and we have two or more of those together, we have a quaternary structure. All right, this is a quaternary structure, and it's telling me 1, 2, 3, 4 of those proteins are together. Is everybody following me? Now, they're trying to represent something else by using the purple and the gold color. Do you see anything being associated with the purple and the gold? Alpha and beta. What about one side versus the next? They're opposite. All right? Now, in the middle, okay, they refer to this as a globin. This purple is the globin, this gold is a globin, this purple is a globin. So 1, 2, 3, 4 globins. In the middle of each one, what do we find? A heme group. This is the structure of the 1, 1, 1, 1 heme. What is right in the middle of the heme group? Iron. Cha-ching. Iron sits right in the middle of the heme group, which sits right in the middle of the globin. All 4 of them have their own heme group. How many of these, because this is a hemoglobin, okay? How many of these were in one red blood cell? Over 280 million. This heme group, the middle of it for the iron, okay, what is it like to bind? Oxygen. So that tells me that for every hemoglobin that's existing in that red blood cell, it can hold up to how many oxygens? 1, and then if I could have 4 of them, how many oxygens can be held? 4. Somebody do the math of 4 times 280 million. Don't even go there with me, okay? But are you getting my point? Okay? Now, it doesn't mean that every single one of the heme groups is connected to an oxygen, okay? Doesn't mean that. It says it can carry up to 4. Okay? Now, we can bind CO2, but notice how much of it wants to bind. Roughly about 5% of what's in the blood. Therefore telling me the majority of the CO2 by way of the bicarb. Now, the heme group is termed a non-protein moiety, a non-protein piece, okay? And it's going to have iron at the center to pick up an oxygen. If someone is low in iron, what is this going to do to the ability of the hemoglobin to transport it? It's going to decrease the ability because the iron is not available to attach to the heme group, and therefore it's not picking up oxygen. So therefore iron becomes very important in the function of our hemoglobin molecules. Am I right so far, Rebecca?
Is that why people with anemia are really cold? Because their blood's not going?
The blood is circulating, it just doesn't have anything to drop off at the tissue. Well, it doesn't have as much to drop off at the tissues for the tissues to carry out their metabolic functions. So it's actually at the tissue level, at that cellular level, we're not getting any type of production. And therefore, yes, they're going to be cold because carrying out chemical reactions affects the body heat of the body. And if tissues don't get enough oxygen, they're going to die. So when we look at oxygen amounts within the body, oxygen amounts, the red blood cell count, and let's stop right there, because you can actually have a red blood cell count done, okay, that can actually try to determine the number of red blood cells you have in your body, okay? Now, the red blood cell count and then hemoglobin concentration are going to tell the amount of oxygen the blood can carry. The higher the amount of each, the higher the amount of oxygen that can be carried. As simple as that. Can there be overproduction? Definitely. Okay?
If you have too much oxygen.
We're going to actually talk about that. We're going to talk about it. Now, everybody's heard of hematocrit, right? Okay? Of course, hematocrit is where we're checking to see what is the amount of the red blood cells. What is the percentage in that total blood volume that is red blood cells? Okay? So they're not looking at the buffy coat, they're not looking at the plasma, they're only looking at that red blood cell section. In men, roughly 42 to 52% of their total blood count should be red blood cells. In women, about 37 to 48%. And that number will change according to age. For example, the older you are, you're not menstruating. Okay? So your blood loss is less. Okay? Now, the hemoglobin concentration. Hemoglobin, men should have about 13 to 18 grams per deciliter. Women, about 12 to 16 per deciliter. red blood cell count, in other words, how many are actually present, and don't ask me about the math, how they do that, because I don't want to know. All right? I don't want to be the one who gets punished to count the red blood cells of somebody's blood sample. Okay? Men should have between 4.6 to 6.2 million red blood cells per microliter. Females, 4.2 to 5.4 million per microliter. Now, when hemoglobin contains oxygen, with this hemoglobin molecule, with the heme groups, with their iron, okay, when these have oxygen attached, this is going to be known as oxyhemoglobin because it's got oxygen, right? Okay? Roughly about the 280 million per red blood cell. At the point that red blood cell has oxygen, okay? Meaning it has gone through the pulmonary circuit, has returned to the heart, left by way of the arteries to go to the tissues of the body. This is oxyhemoglobin. At this point, blood is bright red. When the red blood cell reaches the capillary bed and an artery meets a vein and oxygen gets squished off, we now have deoxyhemoglobin, meaning no oxygen, or very little, okay?
Because some always stays.
Hmm?
Because
Some of it stays. Sometimes there can be 100% drop off, but for the most part, that's not always the case. The tissues would have to actually be very highly metabolic active. Say, for example, the skeletal muscles in the legs of someone who is mountain biking, or the chest and the arms of the upper body of a weightlifter. Okay, the tissues will be extremely metabolically active, and there could be 100% drop off. And she's respiratory therapy, so that's why I was kind of like, no. Okay. At this point, blood is much darker red. Because Charity, our idea about blood, as we look, we think we see something blue, right? Is it blue? No. Whether you talk arteries or veins, blood is red. The difference is when we get to the blood that has lost its oxygen, based on this darker red color, it actually takes on the appearance of being blue to purple.